We got carbon-hydrogen bond. We need to break it to make the carbon-chlorine bond, right? So think about what has to happen. In order to make this from that, you have to break the carbon-hydrogen bond. You also need to break the chlorine-chlorine bond, right? So we need to break the two bonds. So you break the chlorine-chlorine bond, you got to provide 58 kilocalories, which people already measured. In order to break the carbon-hydrogen bond, you have to provide much bigger energies, but that has been measured already. So if you provide 162 kilocalories, which is sum of those two, then you can atomize these all the components. They all become variable. Right? Then what happened was you basically make the HCl by having the hydrogen and chlorine comes together. So that the break, that's about 103 kilocalories. When you make it, it releases about half of the amount, right? That's much energy is required to break a bond. When they make a bond, this much energy is get released, right? So that is by making HCl, you release 103 kilocalories. By making carbon-chlorine bond, you release about 84 kilocalories. So all together, it becomes a negative 107 kilocalories. So this is almost like keeping the balance. In order to break these two bonds, that much energy is required. By making these two bonds, that much energy is received. You add them together, that's going to be negative 25. This is something we can calculate from the table. I told you that heat of delta H for the chlorination of methane was measured to be negative 25.9, which is a very, very close number. What that means is, if you know the bond dissociation energies, you can calculate any chemical reaction, how likely that will happen or not. What we want to do is try to calculate how much energy difference between those two. One, radical to carbon number one, and the radical to carbon number two. How much energy difference between those two? So this is a first propagation steps of the chlorine radical picking up the hydrogen from number one position. It's the first propagation step of the picking up the hydrogen from the second positions. I mean, that type of condensed formulas is hard to read. That is this hydrogen on the secondary carbon that becomes a secondary radical. That's what it is. You already know what to do. You're going to focus on which bonds are made, which bonds are broken. And this was a little different from what we did. You've got to look at things carefully because this could be something that you're going to see and you determine how you do it. It's not always the same way to doing it. Let me tell you what is the difference between this one and the one we did previously. First of all, this is a propane. We're going to break the bond between the carbon and the hydrogen bond of the carbon number one. So these bonds are getting broken. So you're going to provide that much energies to make this happen. And then the chlorine radicals there. Chlorine is already given as a radical. So we don't have to break the chlorine bond that we did before. These reactions already provided with a chlorine radical. So you don't have to break the chlorine. So that's why the chlorine comes not there. But we do form HCl because it wasn't there. It formed HCl. So HCl needs to be formed. When it forms, it releases about 103 kilocalories. Right? So by adding these two, total energy difference about negative 5 kilocalories. The one in the middle position, carbon number 2, it takes less energies, but it produces the same HCl. So if you do that, you found that it's releasing more energies, minus 8 kilocalories. So these ones are more exothermic than the other one. These ones are more spontaneous than the other one. So that's why this happens more than the other one. That's kind of what we get. Just to show you the difference between what we did for the bond and the dissociation calculation. Remember that this reaction we did before, it was we need to break this one, so that much energy is required. We need to break the chlorine bond, so we get to add that. But it makes this bond, so we release that much energy by making this bond. It makes that bond, so it makes this much energy, but it makes this bond. So we added all 4 terms and then get the energy differences that's delta H. This one is different from this one. Can you see the difference there? So you gotta look at carefully each reaction we provide you to calculate delta H from the bond dissociation energies. It's not always adding all the terms that you see like here. Some already came as a radical, so you don't have to correct the chlorine part because that's already done. So we don't need to do these steps. And then we're not forming this bond either yet. So that's why these terms are not there. You only need to focus on what's actually getting broken, what's actually getting made for a particular reaction that we provide to you to make the right calculation, not all 4 terms. I hope that you see the difference between why these terms just have 2 components here, why there has 4 components there.